Hello, everybody, and thanks for being here. My name is KiarashRezaei, and today I'm going to present our paper titled Generative Explainability for Next Generation Networks, LLM Augmented XAI with Mutual Feature Interaction. So this work is a collaboration between researchers from Chalmers, SUPSI, Politecnico Milano, and Tilburg University, and this work was partially funded by Vinnova, Sweden, and Celtic Next. Let's start with the presentation. Okay, so I'm going to start with our motivation, which is explainability in network automation. In this slide, what you see is a general network automation loop that starts with sensing, prediction, then decision, taking an action, and feedback. So in modern networks, machine learning and AI models are vital component of this loop. And to be more specific, they are involved more in the prediction, decision making, or taking action steps. But unfortunately, these AI models are black box, meaning that the network operator cannot understand why a decision was made by these models. So that's why integrating explainability is important to make AI decisions more interpretable and more trustworthy. So XAI can be integrated into these models generally in two ways. The first one is intrinsic, which is built into the model, and the second one is post hoc, where we explain after the model predicts. So intrinsic explainability works when your model is simple, for example, a decision tree. But in modern and complex and also dynamic environment of networks, we need more sophisticated models like neural networks. And that's why often researchers, including us, focus on post hoc methods. So here in this slide, we see a local Shapley additive value, which is a post hoc method. It is local in a sense that it provides explainability for based on each sample. So figure A, you are seeing feature influence plot, which shows how much each feature contributes in the prediction of our machine learning model. And figure B is feature interaction that shows how much two features jointly contribute to the prediction. So as you can see, these are typically represented as numerical values or heat map, which are powerful, but they are not easy to interpret. Also, we need domain-specific knowledge in order to try to interpret them. So that's where LLMs can help by transforming these quantitative values into explanations that are more understandable for human. Recently, researchers started to explore generic LLMs to translate these SHAP influence values into explanations. And in most existing pipelines, as you can see, the LLM only receives the feature influence values, SHAP feature influence values, through a simple prompt and produces the explanations. And these explanations often evaluated based on text similarity metrics, such as cosine similarity. So, for example, these text similarity based metrics try to compute the similarity between the output of the LLM and a reference text in the embedding space. That's essentially checking how similar two texts sound, not how correct or meaningful the output of the LLM is. So that's why we aim to go beyond that and use human-centered metric. I'm going to talk about this human-centered metric in details when I propose our framework. But essentially, we are trying to answer two important questions. The first one is, do reasoning large language models generate better and more faithful explanations than the generic ones? And the second question is, does including mutual feature interactions as well as the feature influence values can even enhance the quality of LLM generated explanations more? So this is the overview of our proposed framework. So it starts with a single sample, then the machine learning model performs a prediction, and based on the XAI method that we have, we extract the feature interactions as well as the feature influence. Then they are both fed into the prompt generation module. Also, we fed the prediction to the prompt generation module. And this prompt generation module has an important role because it produces a structured prompt in a way that it can guide the reasoning steps of our LLM. And as a result, what we have is the explanations. And in order to have a visualization of related information as well as explanations, we integrate a dashboard to the end as the last component of our proposed framework. An important thing about this framework is that it is model agnostic, meaning that it can be leveraged for different types of machine learning models and different types of network automation tasks. We decided to choose quality of transmission estimation use case in optical networks to demonstrate how our proposed framework works. So quality of transmission includes a machine learning model that predicts the signal quality, for example, based on bit error rate. And then, according to the predicted bit error rate, a decision is made that whether a light path is feasible or acceptable, or it is not acceptable. It is an ideal use case because, first of all, it is practical. Secondly, it includes complex and nonlinear feature interactions. Also, we would have quantitative and verifiable targets such as bit error rate. Moreover, from the point of view of network operators, understanding why a light path was rejected is as important as the prediction itself. So let's start with introducing the experimental setup. So as the data set, we have chosen a publicly available quality of transmission data set that includes light path samples. So we have chosen 12 most informative features. As an AI or machine learning model, we have chosen XGB regressor to predict bit error rate. We've chosen XGB because of its great performance in the literature for this specific use case. And as our reasoning LLM, we've chosen DeepSeek R1 with 32 billion parameters and the 4-bit quantized version so that we have an more efficient inference. And we have compared two different frameworks. The baseline framework, which uh, includes SHAP influence values that through a simple prompt is fed into our reasoning LLM. And our proposed framework, which, as I've described, embed both SHAP influence and SHAP interaction values into a structured prompt, then it is fed into our reasoning model. And to compare these two frameworks, we have randomly extracted 40 LLM augmented explanations and from each framework, and these 40 explanations were evaluated by two human experts. And the evaluation, as I've mentioned, is based on human-centered metrics. So we've defined three different human-centered metrics. First one is correctness, which measures how correctly and faithfully the generated explanation reflects the underlying SHAP values. The second one is scope, which basically assesses whether a correct explanation includes the most critical features that influencing the machine learning model's decision. And the last one is usefulness that rates how helpful a correct and in scope explanation is to support human decisions in terms of understanding the model behavior. So correctness and scope are binary evaluation metrics, whereas usefulness scales from 0, means not helpful, to 5, which means highly insightful. And I'm going to jump into the results. So as you can see here in this graph, what we see is a comparison between the baseline framework and proposed framework in terms of the defined metrics. So what we can see that in all metrics, the proposed framework is superior, for example, with 97.5% of correctness, 95% of scope, and an increase of 12.2% in usefulness. So we can also understand that even the baseline model has an acceptable performance. However, the difference in the scope can tell us that the interaction context could perfectly guide the reasoning step of the LLM. Another thing that we observed was the agreement percentage and basically a standard deviation in terms of usefulness. That in the proposed framework, the human evaluators have a higher agreement percentage and lower standard deviation in terms of usefulness. So it shows not only the explanations are of higher quality, but also they are more consistent. I'm going to start this slide with an qualitative example of the proposed framework. So as I've already mentioned, it starts with feature influence values and feature interaction values that are fed into the prompt generation module. So let's talk a bit more about this module because it's an important part of our framework. So it literally includes different components from context, task identification, how to handle the interactions between features. The core part is the input explanations, which the way we embed these values into the prompt. And the last part is the structure of the response. So here you can see the output of the LLM. And I'm not gonna go into the details of this response, but what I would like to emphasize is the fact that it could, the LLM, the reasoning LLM could successfully identify the most influential features, which are feature 4 and feature 6, based on their feature influence plot, which are modulation order and number of spans. Moreover, it could grasp the combined effect of those features which are contributing in the prediction of our model. So it could grasp it from the feature interaction values, SHAP values. And lastly, in the conclusion, it talks about how to possibly optimize the BER of our prediction. And In the next slide, what we have is the dashboard integration. So the way we integrate the explanation pipeline into a visual dashboard so that it can allow operators to view the feature values, SHAP influence, and SHAP interaction values, as well as the estimated bit error rate, together with the explanation of that specific sample. So this hopefully make AI decisions more transparent for the network operator. So I'm going to conclude this presentation with this slide. So we realize that reasoning-oriented models, LLMs, are effective tool for explainable AI in network automation. And our structured interaction-aware reasoning framework could improve correctness by 1.2%, scope by 6.2%, and usefulness by 12.2%. That demonstrates how reasoning and structured prompt can enhance the explanations of an AI model in network automation task. And yes, that's it. Thank you for your attention. I would be happy to answer your questions. So if you have a question, you can contact me through this email or scan this QR code and we can be in touch. Thanks again and have a great day.